Hello. So, in this lecture also we will continue talking about the modal analysis of continuous system. So, in the last lecture we have seen how to use modal analysis to solve free vibration problem of a bar. Here we will try to see how we can use modal analysis to solve force vibration problem of a bar. So, let us consider this example where there is a missile which is in flight and it is excited by an engine thrust Ft. This is excited by an engine thrust Ft and this Ft is acting at x equal to L, because the engine is placed as x equal to L by 2 or at the midpoint of the missile. So, the missile length is L. Now, the thrust that is produced by the engine has the shape of a half sinusoid in time. So, the time variation of the thrust is going to look something like this. So, if is the force, the thrust force Ft, this is going to be a half sinusoid. This is half period of a sinusoid. The time duration over which this thrust is acting is T0 and the amplitude is F0. So, we need to find out the longitudinal vibration response of the missile after this thrust acts on the missile. So, after the complete thrust has acted on the missile, we need to find out the vibration response of the missile. So, it is very intuitive that a missile, if modeled as a longitudinal bar, it is going to be free, right. So, this could be a very simplistic model of a missile. I mean, of course, there is a nose and there is a tail like structure, all those are there. But if I forget about all those and if I try to get a very simple model for the missile, it can be very well modeled as a free bar. So, this is free bar of length L. Now, so the problem boils down to finding out the response of a free bar because of a force Ft acting at the midpoint of the free bar. That is, it is acting at x equal to L by 2 and the time variation of Ft is like a half sinusoid acting over a time span of T0. Now, let us try to solve this problem. How are we going to solve this problem? So, let me write down the equation of motion. So, this is a bar of uniform cross section, if we assume so. Now, how are we going to express Fxt? So, that would be the first question. So, in this equation of motion, Fxt is a force that is acting only at the midpoint of the bar or the missile. How are we going to represent this kind of force in a mathematical form? The best way to represent Fxt as it is acting on the missile is a Dirac delta function at x at L by 2 or a Dirac delta function of x minus L by 2 into f t. F t is the time part of the force, which is an half sinusoid with amplitude f 0. So, this can therefore be written as x L by 2, f t is going to be f 0 sine of 2 pi t by 2 t is 0. So, t will cancel out with each other. So, let me just erase them. So, this is pi t by t 0 and t is between t 0 to 0, because the force is acting only between 0 to t 0. So, my equation of motion now becomes E A del 2 u by del x square plus right. So, a Dirac delta function, if I repeat again, is going to represent a concentrated load or a point load acting at x equal to L by 2. So, Dirac delta function is going to give the spatial distribution of the force. Now, if I do modal analysis of the above equation, what will I get? I will get eta r double dot t So, for every condition we need not follow all the process, all the steps of modal analysis. So, if we have any linear equation, we can directly say that after modal analysis the equation is going to look like this. It will always be going to look like eta r double dot plus omega r square into eta r is equal to q t. So, we do not need to derive it all the time. This is going to hold true for any linear vibrating system, be it continuous system, be it a multi-degree of freedom system. We do not need to derive till the point that the system is linear. We can very well write this equation. It does not matter if the cross section of the bar or the beam is non-uniform, because we have seen that during derivation we did no assumption about the uniformity of cross section. We solved the problem, we derived this equation from a very generalized equation of motion of the system, which had no criteria of uniformity of cross section. So, whatever be the system, till the point it is linear, that is what we are dealing with in this course. It is a linear vibration course. Till the point it is linear, we do not have to bother. We know that whatever be the equation, this is going to be the equation after modal analysis. Now, what is going to be customized to the problem? The thing that is going to be customized to the problem is this natural frequency omega r and the mode shape phi r. This will depend on the specific problem, but otherwise this equation is not going to depend on the specific problem. So, let us find out what is omega r and what is phi r for a free rod. So, for a free rod, if I find out the natural frequency and mode shape, omega r is going to be pi r L root over E A by m, where r can be anything between 0, 1, 2, 3 and so on. So, this is the natural frequency. Mass normalized mode shape now, since this is a, so I should say that this two parameter we know well how to derive it. I am just providing it ready made because I want to shorten the time taken to solve the problem. So, I am sure that all of us will be able to derive this expression for a free rod. Now, the thing that we should notice that unlike the previous cases or the previous example, r equal to 0 is also a possible solution for the natural frequency. That is because this has a rigid body mode. Because it is free, it has a lack of constraint, this will have a rigid body mode and r equals to 0 will denote the rigid body mode. So, in the solution for mode shape, if we put r equals to 0, this is going to become 1, that is we will get a non-trivial solution for the mode shape which is acceptable. So, phi 0 x, which is the, or I can call this as phi rigid body x, is going to be 1 by ml in 1. So, this is going to be 1 after we do mass normalized, this is going to be root over 1 by ml for r equals to 0. So, now how to solve this problem when we have a rigid body mode. So, I have a rigid body mode which is showing in the natural frequency as well as in the mode shape. So, we can see that the mode shape corresponding to the rigid body has no variation in x, which is in tune with the physics, because when it is undergoing rigid body motion or rigid body mode, there would be no deformation of the body. So, the mode shape will not have a deformed shape, but it will have a fixed shape, a constant shape. So, it is going to be something like this itself. So, therefore, I see that the mode shape corresponding to the rigid body is constant and does not have any variation in x. So, how are we going to solve the problem when there is a rigid body mode? So, what usually is done is that the rigid body is separated out from the system and the problem is formulated only or solved only for the flexible mode or the non-rigid body mode. So, therefore, the equation that we have eta r double dot plus omega r square into eta r is going to be 0 to L root over 2 by ml So, this is the expression that we are going to get for r equals to 1, 2, 3 and so on. So, for now we have left away the rigid body mode and we are solving the vibration problem for the non-rigid body mode. So, if I now try to evaluate this integral on the right hand side, what are we going to get? So, we are going to have this expression for mode shape into a Dirac delta function of x at L by 2. So, many of you all might be knowing that this integral is nothing but root over 2 by ml cos pi r by 2 into f 0. This is because the integral 0 to L some function g x into Dirac delta of x minus x 0 dx is always going to be. If any of you all are not acquainted with this part of the derivation, you can just look into any engineering mathematics book where Dirac delta function, the integration of any function with the Dirac delta function is just the value of that function at x equal to 0. Therefore, my equation has boiled down into a very simple equation of omega r square eta r is root over 2 by m l cos pi r by 2 into f 0 into sin pi t by t 0 and t is between 0 to 0. Now, this whole expression is just a function of time, there is no space part in it. Therefore, this is like any other force vibration equation that we have solved many a times earlier, and we are now going to solve this equation. So, if I try to solve this equation, I can use convolution integral or Duhamel's integral to solve this problem. So, eta r t assuming 0 initial condition, we have to assume So, if I assume 0 initial condition, this expression can be written as f 0 into h t minus tau. So, h t minus tau in this case is going to be it is going to be sorry. So, using Duhamel's integral we can say that this is h f tau into h t minus tau. So, if we use h t minus tau in this expression, we can write this as I am taking all the constant terms outside. So, I have so we know the value of omega r, therefore, we can evaluate this integral. Now, the problem has asked us to find out the response after the thrust has been applied, after the completion of the application of the thrust. So, we need to find out the response eta r t for t greater than equal to t 0. So, for that I can write this integral as f 0 so 0 to t 0. So, 0 to t I am splitting between 0 to t 0 sin pi tau by t 0 plus t 0 to t. Now, from t 0 to t there is no externally applied force, so this is going to be 0. So, this whole thing is going to go to 0. So, therefore, we have the expression as so, now all the terms in this integral is known to me and we can solve this integral. So, if we solve this integral, the value that we are going to get is going to be, I have evaluated the integral. So, it is going to look like it is going to look like root over, sorry, or perhaps one should find this out. I mean, it is a huge integral, it is no point in spending time to solve this integral. So, this integral can be evaluated because all the terms are known. So, if we once we evaluate this integral, then the vibration response is going to be u x t, which is summation of s root over 2 by m l sin pi s x by L into eta s t. So, I know all the parameters here. So, I can find out the vibration of this. Now, this is the vibration that where we have not considered the rigid body. So, this vibration response is it's important to know this vibration response, because under this vibration the missile is going to deform axially. So, an axial stress will be strain and stress will be produced because of this deformation, and we need to know whether the missile will be able to or capable of withstanding that stress that will happen due to vibration. Now, there was a rigid body mode which we did not consider. The equation of the rigid body mode, since omega r is going to be 0. So, if we have this expression, so for rigid body mode, omega r is equal to 0. Therefore, this equation is just going to boil down to eta r double dot is equal to 0 to L. I know the rigid body mode shape, which is a constant value, and if it is mass normalized, it is 1 by ml into f x t, which is Dirac delta function of L by 2 into f x t, which is f 0 into sin pi t by t 0 into dx. Now, since this is a constant, we also do not care whether we have to mass normalize this. So, this instead of this I can always write some constant c. So, my expression now becomes c into f 0 into sin pi t by t 0, which also it does not matter if I write this as 1 by ml into f 0 sin pi t by t 0. So, now this equation is just a very simple second order differential equation. I can always obtain my eta r by double integrating this one and by imposing the initial condition and getting the constants, the integration constant that will be arising out of it. So, from this we can also get the rigid body mode as well, but for the vibration problem we are not very concerned about the rigid body mode. For the structural problem we are more concerned by the deformable modes or the non-rigid body mode, which are given by this expression. So, with this we will end today's lecture. In the next lecture we will move on to modal analysis of a Euler-Bernoulli beam undergoing bending vibration. Thank you.